Good morning, Tigers. I'm coming to you today. My co-host, a very itchy doggo, apparently. Padfoot, say hi. Stop being rude. That's nothing to do with you all. Okay. Today we're going to talk about hearing. Yesterday we went over vision and all the aspects of that. Hearing a little bit different, as I think it has a lot more physical nature to it. There's a lot more bones and kind of movement involved, whereas vision is much more based on these like waves coming in and being very quickly turned into neural impulses. The reception aspect of hearing has a lot more moving parts than in vision. So let's get into it. You should, like with vision, you should have gone over the notes, the senses notes. There's a digital copy of that on Classroom. You can print that out at home if you want, or you can do it all on that paper just to kind of walk yourself through knowing all the different parts, understanding all these. Any of these could pop up on the AP test. So understanding each part and knowing what it does is pretty important. So I'm going to walk you through the sensation aspect first. Let's go over that. So put myself down here. So sound waves. What am I floating head down here? Sound waves. Um, what you need to know about like what are we sensing? What are we actually picking up on? Right? Like in vision, we were catching those different pieces of the like spectrum, right? The color spectrum. With this, we're picking up on these waves in the air. So the waves of sound, what we're getting are either you need to understand frequency, pitch, amplitude. And so with these waves, the frequency, basically like how common it's happening, right? Like how often it crosses this middle red line, right? If it's more frequently, right? Like this one, higher pitch, it goes much more quickly. It's hitting that red line more often. That's going to be a much higher sound. Okay. Whereas here, the pitch is going to be much lower because it's slower. The frequency isn't hitting that red line nearly as often. It's not going to go back and forth as often like it would with a higher pitch. And then amplitude, think of that as the distance between that middle line and the top or the crest of the wave. So louder sounds, no matter the pitch, right, are going to have a higher amplitude, meaning they're farther away from the red line. So between these two, think about it for a second. Which one is going to be louder and why? The higher pitch, is also going to be louder because it has a higher amplitude, more distance between the crest and the line. The lower pitch can still be louder. Okay, just because a pitch is lower doesn't mean that the amplitude is also low. We could have this go like way up here, but then not come back down until down over here. It would be super super loud, but also an extremely low sound. You can have that. So, and sound as the measurement is measured in decibels. So what's going on with the general ear and how this works. The outer ear first, we'll talk through outer, middle, and inner ear. Outer ear, you've got these fun things, right? This is what we think of as the ear. We've all got them. This is the pinna out here. Right? The kind of weird cartilages, funky thing that we have on the side of our face. This is what collects the sounds. Those sound waves as they're coming in at different pitch, amplitude, they're collected here. Okay, so this is evolutionarily evolved to catch sounds, to like anything to kind of redirect it into the ear canal. They travel through that canal into the last part of the outer ear, the eardrum. Okay, the eardrum. And this is what you need to specifically be worried about whenever and why like Q-tips specifically say do not use on your ear, even though most people use them on their ear. I also use them on my ear to get earwax out of this canal, but it can be really dangerous. Actually, I have a friend who did this, who like punctured his eardrum using a Q-tip. If you push that in there too far, you can really damage your eardrum and work your way in too far. So be careful when you're doing that. The eardrum is sensitive. So what the eardrum does is what most drums do. It amplifies sound. So whenever this sound comes in through our ear canal, it hits the eardrum. And the eardrum, think of it as kind of like like the lens for the eye. Right? It's what it's doing is it's like refracting and changing and reshaping, like making sure that it like puts it in a code that the rest of the ear can hear. So it channels it down to more to the proper frequency pitch and like makes it so that the rest of the ear, specifically these bones, the middle ear, which we're about to get to, are going to have the proper, they can understand the frequency and the amplitude and the pitch of the sound wave. So after it goes through, hits the eardrum is going to be connected to the hammer, anvil, and stirrup, or the middle ear. These are the different parts of the different bones in the middle ear that are going to vibrate based on the eardrum. So the eardrum catches the sounds and starts like vibrating. Okay, it's going to send it into these muscles or these bones on the inside. So these are bones, or physical bones. They're very small, very fragile, and what they do is they're going to amplify. They're going to make it even louder. Right, and so the reason that is because in the next part, right, when it gets to the next portion of the brain, the inner ear is fluid filled. And if you've ever been in water, like you know that if sound doesn't travel nearly as quickly, it doesn't travel quite as easily through water, so it needs to be louder. So for the part of the inner ear to be able to actually understand what's happening, you've got to have much more amplitude, right? It's got to strengthen it. So hammer, anvil, stirrup do that. They take the eardrum and make it even louder. Think of it as like a speaker taking the like impulses that you've got, the sensations, the sound waves, and then blasting them into the inner ear. So all of these amplify the sound waves, sending it into that funky, and this is like a unfolded version of it. You've seen it before. Let's see if we can get up here. Yeah, the snail looking thing. Right, that's really the only way to describe it. The cochlea. So we've got it unfolded here. The cochlea is kind of the magic. This is where that second step of transduction happens. Remember, transduction is with all of the different parts. You've got, in this case, the reception being the sound waves, the eardrums, the hammer, the anvil, the stirrup, all of those receiving the impulses, the sound waves, the sensations. And now the cochlea is going to transform it, second step of transduction, and begin the process of sending that through these nerves towards where it needs to go. We'll get there in a minute. Think about where it needs to go. So, those bone vibrations in the hammer, anvil, and stirrup send it into the cochlea. What's happening in this weird, funky snail thing is that it is fluid filled, and it has within that fluid this basilar membrane. And in this basilar membrane, it has all these little hairs, and these hairs are basically catching on to the frequency, the pitch, the amplitude, and kind of like the rods and cones in your eye, these hairs are sensitive to the different sounds and understanding what's happening. And those hair cells receive what's happening, transform it into action potentials that can be coded and then understood in the auditory complex. Sorry, auditory lobe. Man, struggling, y'all. So, bone vibrations, cochlea, impulses in the basilar membrane, sends it along to the temporal lobe. All right. No. Yeah. So again, that pathway, catch it here. It works its way up through, as you know, the thalamus. Catches on the thalamus, works its way over to the eventually auditory cortex. This will honestly talk a little bit more about in the other senses. I think it's in that part of the textbook actually, but I wanted to mention it here because it is a part of the ear. The ear is what does this. In that inner ear, yes, we hear and we sense and we perceive sound, but we also, the inner ear plays a vital role in your balance and your dizziness. it has this interesting part of the inner ear that basically think of it as like a sealed off water container. And it is constantly managing our position, our movement in the world. Anytime that your head, your body, anything is moving around, think of it as like sloshing around, right? If you have like a water bottle that's see through and you like move it back and forth, the water moves. If they consider then if that water bottle was filled with like, hairs and membranes that could sense what was happening, right? They could sense the movement and they could read the direction and the position of that water bottle based on where the water was. So within these semicircular canals, that's like that water bottle. It's holding on to that information, but it has sensors or little hairs all around the outsides. And when the fluid moves, that stimulates it and tells us where our body is. And this is crazy fast. This all happens often without us even knowing it. We're able to basically working like interneurons. It blasts messages to our body. And when we're falling, this is what tells us to quickly put our hand out before our brain even processes the fact that we're falling or that something's coming at us. This is something that can like recognize our changes, right? And a lot of the reasons why we get dizzy is because we move it too quickly. Right? Think about that water bottle. If you take a water bottle and flip it upside down really quickly, it doesn't just go straight back to normal. It sloshes back and forth and has to slowly get back to where it is. So this is where you get that dizziness, vertigo, stuff like that. We'll mention that a little bit more when we get to other senses. So what can happen when we receive hearing? What happens with that information? We can get a couple different types of damages. So two that you really need to know. Sensory neural deafness is the biggie. This is the most common. This is the one you need to be worried about. This is what happens when you have prolonged exposure to really, really loud noises. Going to concerts, not just a good place to pick up the coronavirus, it's also a good place to pick up deafness over time. So when noises are too loud, the decibel levels are too high. If you are exposed to that over the course of your life, you have a much higher chance of damaging those nerve cells and eventually not being able to hear appropriately. For professional musicians, they're like 8 times more likely to have serious cochlear damages and eventually need an implant. So what they eventually have to do is put these cochlear implants under our ears. They put this like device around the back of our ear that then stimulates the temporal lobe and has to basically fake it the messages that the cochlea does and send that to the brain. So be careful with your hearing. Do what you can. Yes, you're young. You're going to go to concerts. You can hear things fine. I've been to plenty in my day. But protect your hearing. It cannot regenerate. Right? Most of the other parts of our body can fix themselves, can regenerate. Any damage you do to your hearing is permanent. So be careful with that. It's not just exposed noises, though. It can also be, hereditary. It can be things that you're born with. Children, animals even can often be born with cochlear damage or borderline deafness. And kids, much like with language and vision and anything else, have a critical period where if you give them a cochlear implant within the first few months of life before they're 1, then that can stimulate the brain and have it develop normally. But if it doesn't develop normally, then for the rest of their lives, even at the later point of cochlear implant, they won't have appropriate hearing. That brain will not develop appropriately. Second is conduction hearing loss. This one is physical. So that's the bones, right? The hammer, anvil, and stirrup, right here. If some form of damage happens to those, right? If you get like the actual like concussions can often cause this, or anytime even falling damages, so physical damages, we're going to have trouble with specifically really soft sounds, right? Things that aren't very loud. And so simple hearing aids that go inside can cause this conduction hearing loss, right? You don't need the cochlear implant, which is the one that goes around the back and often goes up to the top. Just a hearing aid can kind of go on the inside to just amplify and make things louder. Pitch, how we hear that. So this is just a little bit more example. If you want to do a test, we did kind of a hearing test that did that did both low and high frequencies. Here, this hearing test does a really good job of going through like the higher ones that you can actually test your age for your ears. I had 24-year-old ears, 5 years younger than my ripe age of 29. So it's worth a test if you want to click through that on your own. So how we hear pitch, we're going to talk about high and low pitches. The high frequency or high pitch that they use that is known as this place theory. So consider this a like unspooled or kind of a run out cochlea. It has the basilar membrane, all of these different hairs, and the hairs at different parts of the cochlea are stimulated by different frequencies. So extremely high frequencies hit one part of it, extremely low frequencies hit another part, and these nerve signals can translate that and turn it into action potentials to go onto the brain. So different parts of the cochlea are stimulated based on different sounds, different frequencies, and the brain can interpret that and it understands, oh, this part of the cochlea was being stimulated. That means that this is a high pitch. Oh, this part of the cochlea means this is a more low frequency, low pitch. So this works the vibrations and tells us and allows the brain to translate that and understand it. The issue is that with extremely low pitch sounds, it doesn't really help us understand where they're localized. So we have to, much like in vision, pick up a second theory for that. So this is our high frequency. For low frequency, you've got the frequency theory. And the way this works is that the like basilar membrane, this is inside the cochlea, is going to vibrate and send neural impulses at the same rate of the sound rates. So it's more of like alternating, firing to achieve higher combined frequency. This is the like a matching, right? So this is the frequency theory says it's like the whole thing at once. You're not just looking at this and that. It's that the basilar membrane's vibrations and that it's matching the rate of the entire sound wave. So we're both looking at like the high, which is going to give us like specific details of the pitch. It's going to work especially for really, really high frequencies, but for low frequencies, you got to look at the big picture. It's kind of how our brain does that. So we're going to call it there. This would have been a fun activity we could have done as a group, but we can't. So maybe try to get your family members to take part in some psychology experiments with you if you so choose. But just recognize we have the ability to locate sounds. Think about, again, if we had in our crowded room, I picked out one student and said, hey, I want you to tell me close your eyes. Everybody around you rearrange. The entire class rearranges except you and whoever your good friend is in that class. I'm going to say everyone is going to say 5 words to you at a very normal sound, and you would have to locate your friend's voice in the midst of that and point it where they were. You could do that, right? Like even in the midst of a crowded room, you'd be able to recognize where people are. And we have that capability because we have 2 ears, right? If we just had one, that would be difficult. Think if you had to close one off, you would have you would have like a difficulty hearing things over here. If you would assume like just about everything was coming from somewhere. So our brain, using both lobes at the same time, interprets where the sound is coming from, and then what it looks for is like basically like a shadow. It looks for the part of the brain, it looks for the part of the cochlea that's not being stimulated, the part of the temporal lobe, auditory cortex, that is missing information. So if the sound's coming from this way, like your shadow's kind of on the back of your head, your ears are probably picking it up relatively equally. That tells us it's in front of us. So it translates and figures out where things are. So that is hearing and balance.